Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 20, and it is entitled Newton's Third Law and Freely Falling Bodies. Two unrelated topics. We'll take them one at a time, beginning with Newton's Third Law. I don't care for the sketches made by your textbook authors, and so I'll try to illustrate an alternate way of sketching action and reaction pairs of forces. We'll use their examples in our own diagrams. A popular statement of Newton's third law is this: for every action, there's an opposite and equal reaction. But I don't think that's a very useful way of stating the third law. I like another way better. If object A pushes on object B in one direction, then object B pushes on object A with the same amount of force in the opposite direction. These forces are simultaneous. There's no delay between when one force begins and the other force. These are acting at the same time. A force is an interaction between two objects. It's impossible for the objects to interact without sensing one another, and for this reason we say that forces always come in pairs. If one object feels the force, then the other object also feels the force. The force will influence how the objects move, but that's not the focus of this lesson. Rather, what we wish to do is to identify the forces. We'll come to call one of the forces in this pair the action force, and the other one the reaction force. Now, we've already alluded to this interaction of force pairs in the way that we've been writing our forces. If we have a wagon being pulled along the ground at constant speed, we identify the forces acting on the wagon. The normal force is the ground pushing the wagon up. We call the weight the earth gravitationally pulling the wagon down. The pulling force was Haynes pulling the wagon at some angle theta, and we call the frictional force the surface of the ground pulling the object in the opposite direction to the wagon's motion. In this lesson, we want to focus on what we'll call the reaction force. To make this more concrete, I would like to take a look at a situation of the Earth and the Moon gravitationally attracted to each other. The Earth and Moon pull each other with a mutual gravitational force. We call this the universal gravitational interaction, and with the right data we can, and will in a future lesson, compute its magnitude. Right now, though, let's not worry about the numbers. Let's focus our attention on the forces that are acting on the Earth and on the Moon. Let's call the Earth object A and the Moon object B. The Moon is attracted toward the Earth through its gravitational force, and I'll indicate that with a force vector pointing in the direction of the force along the line adjoining the centers of the two objects. I'll call this gravitational force the force on object B due to object A. The notation is F with a subscript BA, where the subscripts indicate the interacting objects. The first subscript indicates the object experiencing the force, and the second subscript indicates the object exerting the force. So FBA is the force on object B due to object A. Now, the Moon isn't the only player here. The Earth also feels this interaction, and we'll call that force FAB, the force on object A due to object B, and we'll illustrate it with a vector 2. The lengths of these two vectors should be identical, showing they're equally strong. They have the same magnitude. The directions of these two forces are opposite each other. Now, you might say, well, why don't we see the Earth moving in response to the Moon's force? And the answer to that question is that the Earth is much more massive than the Moon, so we notice that force on the Moon more than we notice it on the Earth. But the Earth still experiences that force. Now, we would say these two forces are action and reaction pairs. The two forces are equal in magnitude, and they are opposite in direction. It would be tempting to say that these two forces cancel each other out, but that would be incorrect. The reason these two forces don't cancel each other out is that these forces act on different objects. One object is the Moon. The other object is the Earth. These are two different objects. For multiple forces to be able to cancel each other out, the multiple forces must be acting simultaneously on the same object. In the case of the gravitational interaction between the Earth and the Moon, one object feeling the force is the Moon. The other object is the Earth. Even though the gravitational force felt by the Moon is equal in magnitude and opposite in direction to the force that's felt by the Earth, these two forces do not cancel each other out. They don't balance each other out because the two forces are acting on different objects. Let's now take a look at a more complicated example. Let's suppose I have 3 stacked blocks with block number 1 being pulled by a rope, as in this diagram. Let's suppose that block number 1 sits on a frictionless floor. Let's further suppose that the surfaces between the blocks are actually rough, so that friction does act between those blocks, allowing the blocks to move together as a unit. Let's see if we can identify the forces acting on each of these 3 blocks, and then let's see if we can identify which ones might be action and reaction pairs. This is going to be a complicated set of diagrams. I encourage you to sketch it along with me as we go. I'll be strategically using color to effectively try to help keep things straight. Let's begin with a free body diagram of block number 1. One force we can definitely identify is the rope, which I'll indicate with an R, pulling on block number 1. F1R indicates the force on block 1 due to the rope. We'll call this the pulling force. The rope pulls block number 1 to the right. Another force on block 1 is its weight. The earth, E, gravitationally pulls block number 1 downward. There's the normal force. The floor, F, pushes block number 1 upward. Now notice in this diagram that F stands for floor and not for friction, because we've said at the start that the surfaces between the floor and block number 1 are frictionless. Now, block number 2 exerts some forces on block number 1. Block number 1 feels pushed downward by block number 2. That's not a gravitational interaction. Rather, it's a contact force. It's a type of normal force because the bottom horizontal surface of block number 2 exerts a vertical force on block number 1. But that's not the only force that block number 2 exerts on number 1. Number 2 is being dragged along by block number 1 due to the friction that's between the 2 surfaces. This means that block number 1 feels a retarding force due to the presence of block number 2. And so we'll label this interaction and call it a frictional force. You'll notice that there's more than one normal force in this diagram. Gosh, Mr. Haynes, this is a complicated free body diagram. Yes, it is, and it's one that has appeared on previous College Board exams, and that's why I've chosen it as an example. It may seem a bit bewildering, but I hope it'll help you as we go on to analyze different situations. Let's move on to sketch a free body diagram of block number 2. Block number 2 feels several forces. One of them is its own weight. The earth, E, gravitationally pulls block number 2 downward. In addition, block number 2 is supported by block number 1, and since block number 1 has a horizontal surface pushing vertically upward on block number 2, this is a normal force. Looks like there's a pair of forces that appears now, acting on 2 different objects, block number 2 and block number 1, that have the same subscripts in opposite order. Can you see F21 and F12 in these 2 diagrams? It turns out that they are action and reaction pairs. They're equal in magnitude and opposite in direction, acting on 2 different objects. That's why I've chosen to sketch them using the same color. Let's go on. Block number 2 is accelerated to the right as a result of the frictional rubbing that occurs between it and block number 1. It is that frictional force that causes block number 2 to change its motion, going from a resting position to a moving situation. It's static friction because there's no relative motion between the surfaces. Now block 2 feels some forces due to its interaction with block 3. Block number 2 is pressed downward by block number 3, another normal force. And block 2 is retarded somewhat in its motion due to the fact that it must drag block 3 along with it. So there's friction between 3 and 2. So those are the forces acting on block 2. Let's move on to block 3. Block 3 feels the earth, E, gravitationally pulling it downward, the weight force. Block 3 is pushed upward by block 2. Since block 2's top horizontal surface pushes upward vertically, this is a normal force. Finally, block 3 is dragged along by block number 2 due to the roughness between the contact surfaces, and this is a frictional force. Now, what kinds of questions might be asked about this situation? For one thing, you might be given the tension in the rope, essentially the magnitude of the pulling force, and the masses of each of the blocks. You might then be asked to find the acceleration of the system. Another question you might get is, what's the minimum coefficient of static friction between each of the blocks in order to prevent them from slipping during this acceleration? You might be told that the frictional forces are actually insufficient to keep the blocks moving together. Given such and such a coefficient of kinetic friction, determine the resulting acceleration of each of these blocks. And I would suggest to you that these would be complex problems to solve. But I'd also suggest that the information contained in these free body diagrams could assist you as you try to unpack those sorts of problems. Instead of asking those nasty questions, I'd like to pose some Newton's third law questions. I'd like to ask this: of all these forces that you see in these free body diagrams acting on block 1, 2, and 3, which of these forces are action and reaction pairs with each other? I've already tipped my hand a bit in something that I've indicated earlier, and I've tried to use color to help address this question. To know which are action and reaction pairs, you need to know what two objects are interacting in each force, and you need to know what the directions of those forces are. Let's recall our scheme for identifying action and reaction pairs. Newton's third law tells us that one of the forces, the action force, is object A pushing object B in one direction. Its reaction force is object B pushing object A in the opposite direction. So let's apply that scheme to answer the question: which of the forces in these diagrams are action and reaction pairs with each other? I claim that there are several. Think about the interaction between block number 1 and block number 2. There are two action-reaction pairs between them. One of them is the normal force. Block number 1 feels a force due to block number 2 in the downward direction, and block number 2 feels a force due to block number 1 in the upward direction. Since these two forces connect the two objects to each other, acting in the opposite directions from each other, then they're action and reaction pairs, and they'll be equal in magnitude. However hard block number 2 pushes down on block number 1, then that's how hard that block number 1 is going to push up on block number 2. We'll call this action and reaction pair number 1. There's the frictional force. Block number 2 feels pushed by block number 1 to the right, and likewise block number 1 feels pushed by block number 2 to the left. We'll call this the second action and reaction pair. Now, can you spot some other action-reaction pairs? Here's a hint. Look between block number 2 and block number 3. Pause this screencast for a moment and try to identify the other action and reaction pairs. Hopefully, you found two action and reaction pairs between block number 3 and block number 2. There's the normal force. Block number 2 feels block number 3 push it downward, and block number 3 feels block number 2 pushing it upward. So there's action and reaction pair number 3. And finally, there's the frictional force. Block number 3 feels pushed by block number 2 to the right, and block number 2 feels pushed by block number 3 to the left. There's your fourth action and reaction pair. Notice that the action-reaction pairs we've circled don't encompass all the forces that are sketched in these diagrams. There are other forces involving other objects that are not sketched in the free body diagrams of block 1, 2, and 3. We're not going to worry about these for the moment. Instead, let's look at one of the text's examples. Example 20.1. A weight is suspended from a rope that is attached to the ceiling. Draw and label all the action and reaction pairs. Now, I don't care for the text's diagram, so I'm going to sketch my own. You'll notice that I have four objects: the ceiling, the rope, the weight, and down here at the bottom, the earth. I want to explode these objects so that I can see them individually. For the sake of simplicity, let's assume that I've got a weightless rope. In other words, I don't have to worry about the gravitational attraction between the rope and the earth. I want to concentrate on the rope and the weight specifically, but let's see if we can get action and reaction pairs. Let's start with the weight. The weight experiences two forces. The earth pulls it downward. That's what we call the weight of the weight. That's kind of an awkward wording, but there it is. And the rope pulls upward on the weight. The rope feels some forces. The rope feels the weight pulling it downward, but it also feels the ceiling pulling it upward. Now the ceiling feels a force. It feels pulled downward by the rope. That's another tension force. We could possibly say that there's an interaction between the earth and the ceiling, but we're not going to worry about that interaction in this because I'm focusing on the weight and on the rope. There's one more I want to sketch. That's the interaction between the weight and the earth. The weight actually pulls the earth upward. Now I want to identify the action and reaction pairs. I see that I've got an action and reaction pair there. The weight force, in which the weight and the earth are interacting with each other. There's this tension force where I have the weight and the rope interacting with each other. And there's this other tension force in which I have the ceiling and the rope interacting with each other. Those are the action and reaction pairs that involve the weight and the rope. Once again, I'd like to write down an important point. Action and reaction forces do not cancel or balance each other out because the forces act on different objects. The action force may balance some other force that's acting on the object, but the action force cannot balance the reaction force. They cannot cancel each other out because it's not acting on the same object that the reaction force is acting on. Young students frequently think that because these two forces are equal in magnitude and because they're opposite in direction, then they must be able to cancel each other out. Many people will answer incorrectly test questions about that issue. I hope you're not one of them.